In this video, I'm going to drive a stepper motor using embedded Linux, and I will use the Beaglebone in particular. This task is useful for robotic type applications or for applications like 3D printers where we need to drive stepper motors. First in this video, I'm going to briefly review stepper motors. Then I will explain how the EasyDriver, which is an open source hardware stepper motor driver, can be used to keep your Beaglebone safe, especially considering we'll be using relatively large voltages and currents. I've written a C++ class that allows you to drive the EasyDriver board within embedded Linux. And finally, I'll show an example of a circuit setup and my code running. So what is a stepper motor and why are they useful? Well, the key feature, which the name suggests, is that they step or rotate a little bit when pulses of electricity are applied. Low-cost stepper motors, such as the one I use in this video, typically have 200 fixed angular steps for a full rotation and have a step accuracy of 1.8 degrees per step to plus minus 5%. However, the good thing is that there is no accumulated error, so when you rotate 360 degrees after 200 steps, it will still only be out by plus minus 5% of 1.8 degrees, so that's about plus minus 0.1 degrees. Because of this, stepper motors are generally operated in an open loop, meaning that we don't have to have a feedback loop in order to determine the position. This is not the case with DC motors, as while DC motors can be positioned with a greater accuracy, they accumulate errors over time and so must be combined with shaft encoders, which means that we need a closed loop arrangement that adds complexity to the design. The downside of stepper motors is that they need controllers. They vibrate heavily and they don't accelerate as quickly and are not capable of driving as high a load as DC motors. However, they are excellent for digital type applications where we need to position accurately. A stepper motor has a number of coils that are connected to the stationary body of the motor, which is called a stator, and these are turned on and off carefully in sequence to pull a tooted magnet that is attached to the moving shaft of the motor, which is called a rotor. In this video, I'm using a low-cost bipolar stepper motor. It costs about €12, which is about $15, and it's from Water Rot. It has a surprisingly high torque of 0.23 Newton meters, which is good for the price. The fact that it is bipolar means that it has a single winding per phase, and the current in the windings need to be reversed in order to reverse the magnetic pole, which makes it more complex to drive. It's a 12-volt motor requiring 1/3 of an amp per coil, so for controlling it, I'll use the EasyDriver motor controller. The EasyDriver is an open source hardware stepper motor driver. It is widely available, and the most recent version at this time is the EasyDriver version 4.4, which is available through SparkFun and is about $15, again about €12. You will need one of these boards for each stepper motor that you're driving in your project. It's a flexible board that allows you to drive 4, 6 or 8 wire stepper motors. For a 4-wire stepper motor, you can just connect the wires directly to the board. For a 6-wire stepper motor, work out which 2 wires are the center wires of the coils and then leave them floating, but cap them to ensure that they don't touch each other. For an 8-wire stepper motor, you can connect them in a 4-wire series or a 4-wire parallel configuration. In this figure on the right, I've illustrated a 4-wire series configuration where you simply bridge 2 pairs of coils, giving you 4 wires that can be connected to the board. The board has an output drive capability of between 7 volts and 30 volts, and the current can be adjusted via an onboard potentiometer from plus minus 150 milliamps a phase to plus minus 750 milliamps a phase. The EasyDriver uses the A3967 from Allegro Microsystems, which allows for full, half, quarter and 8-step microstepping modes. It has internal circuit protection including thermal shutdown with hysteresis, undervoltage lockout and crossover current protection. The only thing you definitely shouldn't do is disconnect the motor from the EasyDriver board while it's powered. One nice feature of this board is that it can be driven by 5 volt or 3.3 voltage levels. This is handy for the Beaglebone as we want to use 3.3 volts. So there's a jumper SJ2 that we can solder bridge. It's useful to look at this board because there are higher power versions of this board, and the input outputs are very similar to boards by Polulu Robotics and Electronics. You should be able to adapt the source code in the next part of this video to most of these board types. This stepper motor has 1.8 degrees per step, so 200 steps per revolution. This is quite a common step resolution, but as I said, the Allegro chip has a micro-stepping feature. When we are using full stepping, the two phases are always on and the motor will have maximum torque. If we select half stepping, then the driver alternates between two phases on and a single phase on. The stepping resolution doubles, but the torque is reduced to about 3/4 of its value. Microstepping uses sine and cosine waveforms to step the motor and allows us to achieve very high stepping resolutions, but with a significant reduction in torque. This board allows us to achieve 1/8 of a step, so about 1/4 of a degree per step for this motor. Microstepping results in better step resolution and smoother operation with less vibration, but it does have a significant effect on available torque. The board itself is displayed here, and you can see the 24-pin A3967 IC in the center. I'll go through each of the input-outputs individually to explain their use. Going clockwise, starting with the top left, there's a small LED that activates when the motor power is applied. You can even see this light if you rotate the servo motor shaft manually. The next outputs are the 4 connections to the stepper motor. These 4 wires can be connected to 4-wire, 6-wire and 8-wire stepper motors using the configurations in the figure that I showed you earlier. Next is the percentage decay input that allows you to choose slow, fast or mixed decay using a voltage level on this input. If the voltage level at the input is greater than 0.6 times VCC, slow decay is selected. If it's less than 0.21 times VCC, then fast decay is selected, and if it's between the two of these values, then mixed decay is selected. This factor affects the microstepping performance by reducing the distortion of the current waveform due to the motor back EMF. Grounding this input will choose fast decay. The reset input is next and is active low. If you ground this pin, then it will ignore step inputs and turns off all outputs until the reset returns to high, so ground this pin for regular operation. Next is the enable input, again active low, and if it is set high it will disable the outputs. The step, direction, MS1 and MS2 inputs are independent of this input. For regular operation, ground this pin to enable the outputs. The MS1 and MS2 inputs at the bottom and top of the board are next. These 2 pins allow you to select the microstepping step. As you can see in the table, if these 2 inputs are grounded, then it will be full step. If you connect MS1 low and MS2 high, then you'll get half step, and so on. The motor voltage supply is next. In my case, I have a 12 volt supply connected to these inputs that's capable of delivering 0.33 amps per coil. Next on the bottom right is the direction input that allows us to choose whether our motor is rotating clockwise or anti-clockwise. The step input is next, and that causes the motor to take a single step on a rising edge, that is a low to high transition. The size of this step depends on the microstepping input selected. The ground should be connected to your Beaglebone. The sleep input is active low, and when low allows you to minimize power consumption by disabling most of the internal circuitry and the outputs. You can see this in a minute that when this is called within my code, there is no holding torque. On the bottom left hand corner there is a selection between 3.3 volt or 5 volt logic level control. For the Beaglebone we have 3.3 volt input output levels, so you should bridge this point with solder. Finally, there is a current adjustment pot in the center of the board. You should select minimum by default and then rotate this until you get smooth stepping with your motor at its desired speed. Just be careful with this pot if you're using a version of this board older than version 4.4, as there were some errors in the silk screening or the pot used. So on to my source code. I've made my code available through Git, which is a distribution revision control and source code management system. This repository contains the code for this video and previous videos. I'll update this repository if I make any changes over time. So to download the code from GitHub, we can make a temporary directory. Let's call it temp, cd temp. There's nothing in this directory. And we can clone the repository from the remote site. So we can go git clone git git hub.com/Derek Malloy, DEREKMOLLOY, and Beaglebone. So this goes off, clones into Beaglebone, and downloads the repository to our local directory. So if we go ls, we can see that we've got a subdirectory called Beaglebone. Go into this directory, and you can see here that we've all the code that I've made available for the Beaglebone project, and it includes the EasyDriver.h and EasyDriver.cpp files, which you can use to create your stepper motor project. Here's some different types of stepper motors. For this particular project, I'm just going to use the smaller stepper motor. It's a 12-volt stepper motor, Mercury Motors, and it drives with about 0.33 amps. In this case here, I'm going to use a universal aluminium mounting hub, which looks like this. It's just a small hub, and it has a little Allen key slot on the side just for tightening onto the shaft. It's a circular shaft, so I'm just going to mount this onto the top of the stepper motor. Tighten it with the Allen key. And just means, just means now that I have something where it's very clear that the shaft is rotating. So as well as the 5mm mounting hub, one other thing that I've done is to wire a male header onto the end of the wire. So here I've got my male header, and it's simply soldered on. I've soldered the 4 wires on with a bit of heatsink tubing just to keep the wires separate from each other on the far end. So this just allows me to plug it directly into a breadboard. One thing that's useful to know is that if you're trying to work out, or you don't have a data sheet for your stepper motor, which seems to be quite often the case, sometimes you need to work out which wires are connected to the same coils. One easy way to do this is to actually short across the wires and then try and turn the motor. So if we turn the motor here, it should, if you get a good stepper motor, it should be free turning. And as soon as you short across two of the pairs that are connected to the same coil, you should find that there's a definite increase in how hard it is to turn the actual shaft. So in this case here, I can probably say that red and green are connected together without looking at the data sheet. In this case here, if I touch off these two, we can see yellow and blue. Yeah, definite increase in how hard it is to turn the shaft. So therefore, it's noticeably more difficult. I can say that definitely with some certainty yellow and blue are connected together. So therefore I know in this case here, I could look at the data sheet, but in this case here, I know that red and green are connected to the same coil, and yellow and blue are connected to the same coil. So here's my stepper motor tests, and just before I get started, just one thing to point out is that when we run this code, that I can feel the actual motor is a little bit warm. It's actually consuming power. The way we know this is that the shaft won't rotate at all. Its holding torque is high, and it doesn't rotate at all. When I run the test application, it's going to go forward or clockwise in full step, reverse in half step, forward in quarter step, and then reverse in 1/8 step. And halfway through, I change the speed from 60 RPM to 120 RPM. So I just run the application now. You can see forward, reverse 360 degrees each time, forward and reverse, and you notice the speed change as it went. Then I put in a delay for 10 seconds, and the reason I put in a delay is because I made the motor sleep for 10 seconds. So you can hear there's no holding torque, and I can rotate the shaft freely. Once it's finished, the 10-second delay is over, I can't rotate the shaft at all. Here's one more example of the stepper motor rotating from on top, and you can see the code executing on the Beaglebone on the right hand side. I've secured shells into the Beaglebone so that you can see the code executing at the same time. Even though the stepper motor weighs 200 grams, you can clearly see it vibrating when it rotates. So here's an annotated image of my final circuit. You can see the Beaglebone P8 header at the bottom of the figure, and I've used pins 2 for ground, pin 3 for MS1, pin 4 for MS2, pin 5 for my step, pin 12 for my direction, pin 14 for my sleep. Those wires run directly to the EasyDriver. You can see the 12 volt supply coming in on the left from my power supply. That goes to the 12 volt rail on top and comes in on the top right hand side of the EasyDriver board to those inputs. Finally, you can see the motor pins, the red, green, yellow and blue pins. They run directly to my stepper motor. Finally, I'll show you the source code. So once you've downloaded the code through GitHub, you can build an Eclipse project around it, and that's what I've done here. Here you can see my EasyDriver.h file, my EasyDriver.cpp file. This is where I declare and define a class called EasyDriver that allows us to wrap the functionality of the EasyDriver. This is useful because it allows us to create multiple objects of this class so that we can connect multiple EasyDrivers to the same Beaglebone at the same time. So it can be quite useful. Here's the code that I've written. It really uses this one class here. I have my enumeration at the top, which is just a simple enumeration to define if it's full, half, quarter or 8th step to ensure that we can't choose anything else. And here's the class itself, EasyDriver. So here's the definition of the class between these two curly brackets. So it's class EasyDriver. There's some private, protected and public states. The private states are the pins that define the MS1 pin, MS2 pin, step, sleep pin, direction pin that are passed to the constructor. So we simply store them as states of the class. There's a couple of factors here such as delay factor and microsecond delay, and they're used as states of the class in order to sort out a constant delay or revolution per second that we can use. A state to define whether we're going clockwise or anti-clockwise. We have a speed, step per revolution, there's an internal calculation, and so on. Is the device asleep or awake? So that's our Boolean state here. So the first important function is the constructor. The constructor accepts multiple values. These are the pin numbers, the MS1, MS2, step, sleep and direction pin numbers. These must have been exported and set up before you pass them to the constructor, and I'll show you that in a minute. It also contains two values, the speed in revolutions per minute and the steps per revolution. So in my stepper motor it's 200, but I've set a default value of 200, but you can change that by passing a new value to the constructor. Similarly for the RPM, the speed in revolutions per minute, you can pass a different value to the constructor. 60 is just the default value. So this in the constructor looks like, this function looks like this, where we simply set up the pins as we would have done in previous videos, and we set clockwise to be true. We set it to default to full stepping. The revolutions per minute is the value passed, the speed is the value passed, and we just make sure that the EasyDriver is awake, in other words that it's not set to sleep. The next function, step, accepts a number of steps, but if you don't pass a value, it'll default to 1, so it'll do a single step. We can rotate by a number of degrees, and essentially this is just the same as step, only that it works out what it means to rotate 45 degrees. How many steps is that? And that's just a useful functionality that's been built into the class. Reverse direction just reverses. If it's clockwise, it reverses it. It goes not clockwise. Step mode allows us to set if we're half step or full step. Get the step mode returns to getter instead of a setter. Speed, get the speed, similarly allows us to set the speed and get the speed. Another setter and getter for the revolution, steps per revolution. So again, that'll be 200 in most cases. Sleep, for example, and wake allows us to set the device to be asleep or wake it up. Again, somewhat like a getter and setter. Sleep sets it to be true, to go asleep. GPIO get value, set value sets the pin to be low, which means it's active low if you remember. So it means that it goes asleep. Finally, is asleep returns whether it's asleep or not. And finally is the destructor, which unexports the GPIO pins. So just to check if there's anything important here, the set mode just sets the MS1 and MS2 pins low, low, high, low, low, high, 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 according to the truth table that was on the diagram of the EasyDriver, and sets a delay factor. The delay factor here is just a factor to allow me to know how long I should wait, because if obviously you have to wait longer. If you're doing 8 steps, you have to wait a shorter amount of time than if you're doing 1 step if you want to have a constant RPM. So this delay factor allows me to control that. Set the speed in RPM. I'm going to use a function here called microsleep or usleep, which accepts microseconds, but the value you pass to it has to be a number of microseconds as a long int, which means that I need to know my delay in microseconds. So that means my delay per second is going to be 60 times my revolutions per minute, which is going to give me my delay per step in seconds, times the steps per revolution. So this is, remember, a revolution is a full 360 degrees, so this would be 200 in my stepper motor. It would need to go 200 steps. Finally, this microsecond delay is going to be the delay per second times 1,000 times 1,000, so that's 10 to the 6. So that means, let's say this number here, delay per second, is a very small number. Multiplying that by 1,000 times 1,000 gives us that value as a long int in microseconds, which we can pass to this function here. Step has one thing that's only important about step is that step can be negative. So it means that we can go minus 60 steps, which will go 60 steps in the opposite direction to the direction we're currently traveling in. And that necessitated a second loop. Now there's probably a better way to do that, and you can probably fix it up. But if the number of steps is greater than 0, do the number of steps, go low, high. This rising edge is what causes the step to happen. If we're going in a negative direction, just set the direction, just step in the opposite direction. So set the direction to be high, so switch the direction of the rotation. Rotate a number of degrees is very simply just working out what it means, what a degree means. So obviously if you divide 360 by the number of steps for resolution, 200, you're going to get 1.8 degrees per step. So it means trying to work out what's the closest value to rotate 45 degrees, how many steps that is. So that'd be 45 divided by 1.8. Finally, the unexport would just release these pins and make them available when the destructor of the EasyDriver is called. This EasyDriver class uses the simple GPIO header and implementation that I used in previous projects, and this is the way that we're able to set up and release the pins. The only one here that's added that's different, that may be a little bit different, is GPIO OMAP MUX setup, which is specifically tailored for this particular chipset, so that we can set up the pins as inputs or outputs, or as write only or read only. And I do this in my main function. So in the main function, I call a small function called stepper motor test, and this is just an example of how to use this class. And this is the way that I actually set up the pins to be the correct OMAP MUX setup, so that choose the correct output pins according to the physical pins that are on the device. So GPIO OMAP MUX setup says we want GPMC AD707, which means we want to use GPIO 39 pin 8, and we want to use it in mode 4. So you'll know from previous videos, I have a video on the GPIOs within the Beaglebone, and this is just a function that wraps that neatly. So once you've set up these 5 pins, which are the 5 pins that control the EasyDriver, we pass them to the constructor. So you can see here the 5 pins are being passed as pins 38, 39, 34, 26, 44, and then this is my speed in RPM and my number of steps per full revolution. So this is 60 RPMs and 200 steps per full revolution. You didn't have to pass those values. If I deleted that, that would give me the exact same code. But just to be clear, I left them in. So make sure the motor's awake. There's no need to do that. That's already done in the constructor, but it's just an example of how you can call a function on our object once it's created. We can print out that we're going to start our motor test, rotate 360 degrees forward. So we rotate 360 degrees. Sleep 1, we're just going to sleep between each test stage. I'm going to reverse the direction and set the step mode to be half step and rotate 360 degrees in the opposite direction. So this is to show you that it's working correctly, that we can rotate. Again, sleep for another second. Set the speed in RPMs to 120 RPMs, so double the speed of rotation. I'm going to rotate forward 360 degrees in the forward direction at quarter step. And I do that by reversing the direction again and rotating 360 degrees. So I've doubled the speed and I'm rotating in quarter step in the opposite direction. Again, I sleep for 1 second, and then I'm going to release in 1/8 step, and I'm going to rotate, just to show you, minus 360, which allows us to rotate minus 360 degrees, and I didn't have to set the reverse direction in that case. It's just a case of which suits you better in terms of the state. Finally, I sleep the motor. I put the motor asleep and then sleep for 10 seconds. This means that you'll see in the video in a minute that we're able to, there's no torque on the motor shaft, so it means that we can rotate the shaft freely, which would not have been the case if the motor was not asleep. I can wake up the motor, but it's not important, because in the destructor of the motor 1 call, when the object motor 1 is destroyed, it'll unexport the pin and it will switch back to being awake. Print out a message to say the motor test is finished, and that's the end of my source code example. And the destructor is called when this motor 1 object goes out of scope at this closed curly bracket here. So that's my video on driving a stepper motor using embedded Linux and the EasyDriver board. The open source hardware EasyDriver board and derived versions are low cost flexible boards that can be used efficiently to drive stepper motors without any sort of soft pulse width modulation code. This means that we can easily drive many motors from the same embedded Linux device with relative ease. Hopefully you'll find the source code useful, change it, adapt it to your applications and use it in any way that you wish. I can't guarantee that it's error free, but if you notice any errors, please let me know.